to distribute or to accept and distribute vaccines when they were ready. So everyone's just ready to go. We're just kind of at a standstill right now. See what happens. I was live streaming for 6 hours on election night. That was fun. I had 2 presidential maps. One was what I believed what would happen based on an adjustment. Here's my adjustment. The adjustment was, okay, let's look back at 2016. In 2016, Clinton, the polls showed Clinton in, let's say, Wisconsin. They showed her winning by 5. What actually happened in Wisconsin? She lost by 1. That was a 6-point swing. I did that for every state. I said, okay, what were the swings that happened in every single state in the polls compared to what actually happened in the election? And I took all of those swings and I applied them to, there's the current polls in 2020. This is my research right here, by the way. And I predicted this map right here, the one that I just highlighted. I predicted, based on these adjusted numbers, that, because everyone was saying, oh, Biden's going to win in a landslide. I'm like, oh, it's not going to be a landslide. It's going to be a coin flip. I think I'm right. Because the poll, you know how they collect polls? How do they collect polls leading up to the election? How do they find out people's opinions? What do they do? Do you know what they do? Yeah. Surveys? How do they ask you the survey though? Do you know? No, those are fake. They call you. For the past 100 years, they've collected poll data by calling people. But the problem is, in the last 20 years, we have these nifty devices called smartphones. When is the last time you answered the phone with a number that you didn't recognize? Right? So the thing is, they're not getting accurate data. In these polls, they're not getting accurate data. I know that. I teach statistics. I know this stuff. So I actually made 3 predictions. One, here was the polling based on the map from the polls. Here was my adjusted number. And then I made a bold prediction. I said that Florida would flip, which it did. I said that Pennsylvania would flip, which it almost did. And I said Wisconsin would flip, which it almost did. And so I actually did have Trump winning in my predictions, but I ended up being wrong. But I was pretty close on this. And I'll show you, because again, this is like my bread and butter in terms of statistical analysis. Here are the remaining states, Senate races, and House races. And it's projected to be that. I was pretty darn close to that in my adjusted polls. I don't know. Oh, it's just for fun. That's what I do for fun. Yeah, I also speedrun video games. But anyway, check out my YouTube. Anyway, the funny thing is there are 3 Senate races, and the Senate, even though the Democrats thought they were going to be up like 54, it's going to end up being Republicans 52. And in the House, even though Democrats thought they were going to get 250, they're only going to end up with 222, according to my numbers. It's pretty awesome. Here are my records for this year, and I'm going to have to compare it to the next election in 2018, the midterm election in 2018, but this is how accurate I was in terms of the election. It's pretty solid. I don't know. No one's ever 100%, but I was pretty darn close. I don't know. Feel pretty good about that. I'm going to do a recap video, and then we'll see what happens from there. I don't know. I'm going to be covering the 2018 midterm election or 2022 midterm elections. The funny thing is, everyone is very much on like the post-election, like we're done with it, kind of thing. I'm not. I'm so not. I'm so hyped. I'm hyped for 2022 to see what happens next. But anyway, going back to this. Here's the fact of the matter. People don't understand how the electoral process works. Just because he won on election night or the week after election night, nothing's official yet until the Electoral College actually votes. Fun fact, you don't actually vote for president. You vote for, no. I don't think you understand how the election works. The popular vote does not determine the president.
No, we don't determine the president, but our vote counts for the popular vote.
But the popular vote counts for nothing. But it counts for nothing, though. It doesn't determine anything. See, here's what it actually counts towards. When you vote in the state of New Jersey, you aren't voting for the presidency. You are voting for a person to cast a vote. New Jersey has 14 electoral votes. Those 14 electoral votes are represented by 14 people. These 14 people, there's 14 Democratic people, there's 14 Republican people. And when you cast your vote for the presidency, New Jersey ends up going Democratic. That means that the 14 Democratic electors are the ones that get to cast their vote. And two or 3 weeks into December, those 14 people from across the state will travel to Trenton and officially cast their vote in the Electoral College. That's what determines the presidency.
So there are 28 for us? You said there's 14 Republicans, 14 Democrats?
But there's only 14 electoral votes in New Jersey, which means only one side's going to win.
So are those representatives?
Because New Jersey went Democratic, the 14 Democratic electors are the ones who get to cast their vote. The other ones don't. No, New Jersey's only been Democratic since 1988. In 1984 and before, they was pretty much Republican. It depends on the people. The people vote. The people vote in the state of New Jersey, and the popular vote in New Jersey determines the winner of the electoral votes for New Jersey.
So then our vote does.
Kind of does, kind of doesn't. People misunderstand it. The popular vote means nothing in the nation. The popular vote within the state does mean something.
But then the state still says
Yes, well, the state, then all the electoral votes would then go towards one party, with the exception of Maine and Nebraska. And Maine and Nebraska passed laws to actually delegate their electoral votes in a different way.
But so like now I'm confused. The electoral college, they vote December 14th. Right?
Sure. Or whatever date that is, yeah. Okay.
So what? So like there's nothing more count until like they vote on December 14th.
Correct.
So this is all fake.
No, we're just in a grace period in between. People are calling Joe Biden the presidential-elect, and he is. Okay, he is. But legally, he is not until December 14th.
Right.
Yeah.
So why it's like it all comes down to the electoral in December.
Yes.
And why do we vote in November to get and do that if they aren't if there's a chance they might actually be elected?
The electors in the Electoral College are supposed to vote the way that they're told. They're supposed to. They don't have to, but they're supposed to. Which is why, and people don't know this, in 2016, and this is the last I'll say of this because I do have to get started with my lesson, but in 2016, a lot of people don't know this, but the Electoral College did not vote exactly the way that they were supposed to. There were a number of what they call faithless electors. Faithless electors. Oh, I'm in Wisconsin. Hold on. Here we go. There were a number of faithless electors who did not vote the way that they were supposed to. And when you don't vote the way that you're supposed to, you actually end up getting fined. But those faithless electors, you can see this right here, faithless electors, casted electoral votes for Bernie Sanders, John Kasich, Ron Paul, Colin Powell, and you can't see it, but there's actually a Native American called Faith Spotted Eagle. Yeah, there were 1, 2, 3, 4, 5, 6, 7. There were 7 electoral votes, 7 people who decided not to cast their vote for who they were supposed to.
And wait, there's a specific rules that are supposed to be from the state. Well,
you tell them by voting. Yeah. In New Jersey. Watch, hold on.
But like you could choose whatever. If it really comes down to it.
Yeah, you could. But you're supposed to vote the way you're told. I know, it's a weird process, but that's the way it works. People are like, oh, I hate the Electoral College. Fun fact, I would argue 75% of Americans don't understand the Electoral College. But they're like, oh, I hate it. They should replace it. You don't understand what it is. Anyway, ladies and gentlemen, if you would, I'm going to need those notebooks out and open. Literally, I could talk about this all day. And you know when I talk about this? I talk about it in discrete math. Discrete math is an elective that I teach. And one of the chapters that we cover in discrete math, voting methods. Yeah, fun fact. If you have an election with more than 2 candidates, it has been proven that there is no fair way to do it. Can't do it. No, not even if you have more than 2. Can I tell you why? Sorry, I'm just so excited about this. Who won the popular vote in 2016? By roughly 3.5 million votes, or 3.8 million votes, right? She won by 3.8 million votes. Look, popular vote. Question. Yeah. How many people did not vote for Hillary or Trump? Hold on, I got to get to it now. The question is, how many people did not vote for either one of them? The answer, once I get to the right screen here. Come on, you. There it is. Hillary won by 3.8 million, right? Oh, whatever. Gary Johnson had 4.5 million. Jill Stein had 1.5 million. Evan McMullen had 750,000. There were over 7 million people who did not vote for either one of them. Hillary won by 3.5 million. Okay, but what about those other votes? If it was down to 1 versus 1, we don't know what they would have done. Just because somebody wins the popular vote does not mean that that's a fair election. Especially considering the fact that, did she have over 50%? Nope. So it's not a majority. Anyway, I love math. Back to this. Let's call this Intro to Polynomials. Everything in life is mathematics, whether you want to believe so or not. Everything. And it's quite remarkable how people misinterpret the results of things. And they basically take the headlines and kind of run with it. But they don't understand the fundamentals behind it. Let's talk about what a polynomial is. A polynomial is an equation where all exponents are positive whole numbers. I'm going to show you an example of that in a moment on Desmos. Positive whole numbers. It's going to be very interesting. What is this? What? Sorry, my son's first grade teacher was diagnosed with COVID. Yeah, she says it's unrelated to the children or the school. She needs to quarantine. Wow. Sorry, that was kind of shocking. Yeah. I'm sorry. That was also shocking. Unfortunately, no, I ran out recently. I don't know.
But did my teacher help me?
You can do it.
What?
I'm giving you encouragement. I believe in you.
Okay, well, okay.
I'm sorry. As a teacher, that's how I give encouragement. All right, let's go to Desmos.
I'm struggling over here, and you're just trying to do Desmos.
Oh.
How does this relate to math? You said everything relates to math.
Yeah.
So how does this relate to math?
Well, you're using a piece of paper that doesn't really have that much of an absorbance factor because of the material that it's made out of and its composition.
So how does that have to do with math?
Back to
You should
this.
really get the paper towel.
I should. Here's a linear equation. Now, the interesting thing about this linear equation, ladies and gentlemen, is the fact that it is what we call a first-degree polynomial. It's a first-degree polynomial because the largest exponent on it is a 1. Oh, happy day. Let me change it. I'm going to change it now to this. Stuff that we've been doing this entire school year. This is a second-degree polynomial. This is a quadratic. We've been dealing with these for months. You ready? I'm going to change it again. Let's change it to a third-degree polynomial. Oh, there we go. There is a perfect example of a third-degree polynomial. The largest exponent is a 3. All the exponents are positive whole numbers. This thing is not a straight line, obviously, and it's not a parabola. This thing does all sorts of wacky turns all in the middle. This is where we're headed. We are headed towards higher level polynomials, higher degree polynomials. Third degree, cubics. They're called cubics. Fourth degree, quintics. No, fourth degree are quartics. You don't have to know those names, but fifth degree are quintics. Sixth degree, seventh degree, eighth degree. You can do any degree you want. And I'm going to show you how you can deal with them and how you can solve them and how you can evaluate them. Eventually, how you can graph them. It's going to be phenomenal. Here, watch this. I can make fourth degree. No. Minus x. No, minus 2x. Yeah, minus 2. Look at that. Have you ever seen anything so ridiculous?
Yeah.
Where?
Your face. Oh. Please don't give me attention. Don't do it, please.
For those of you in the chat, you can't see it, but I'm literally crying. How could you see my face?
How could I say it?
See.
See it? I don't have to see much.
Wow.
I'm joking. Please don't give me attention. Let's get back.
I'm trying to come up with a good witty response, but I can't. Did you bring back paper towels? Somebody get the door. So, examples. Y equals 2x plus 1, which is linear. Y equals x squared plus x minus 6, which is what we call quadratic. And here's one, y equals x cubed plus x squared minus 3x minus 2, which is what we call cubic. All of these are polynomials. They are all polynomials. That is what they do. That is how they act. They all do sorts of weird things. They honestly can do anything you really want them to do as long as they are written correctly. But let me show you what you can do with them. Let me give you a different example. I'm going to give you a cubic example, and we're going to talk about what we can do with this. I'm actually going to put this equation on Desmos in a moment so you can see what is going on with it. But this is a basic cubic equation. Again, a cubic equation, you can tell it's cubic. You can tell it's a third-degree polynomial based on the largest exponent. Typically, they are written with the largest exponent first, and then they go down. That's what they do. They all do sorts of different things. Give me a number, positive or negative. Make it small, but don't use like 1 or -1. Make it small. I could do -4. Yeah, we could do 2. We'll do 2. Maybe we'll do 2 in a minute, but we'll do -4s first. All right, let's evaluate this. This is one thing you can do with this. Let's evaluate it at f at -4. This is one thing we can do with this equation. We can evaluate it at f of -4. And I'm going to do that in a moment. Let's take a look at the graph real quick. I'll come back to the screen. So this is going to be, I want it to be red. Make it red. Hold on, y equals 2. That's purple. All right, we'll do purple. All right. So we'll do 3x cubed minus 4x squared minus 17x plus 6. That is awesome looking. And I'll make it f of x for the sake of argument. But look at this thing. Look at that thing. That's amazing. I love it. Look at that purple monstrosity. All right, let's go back to this screen. Let's evaluate it. The easiest way to go about evaluating something like this is simply plugging it in. Plug that sucker in. Be very careful with your parentheses. Parentheses will save your life. And you plug that sucker in, and then you're like, all right, fine. I got to go to my calculator at this point. 3 parentheses, -4 to the third, minus 4 parentheses, -4 to the second. Notice I'm going to zoom in a little. Notice my use of parentheses. Again, minus 17 parentheses, -4, plus 6. Boom. -182. That's fun. But that is what it is. So what we can say is that f at -4 is equal to -182. In fact, -4, comma, -182 is a point on the graph. Input, output. That's what these things do. Fantastic. Let's try it with another one. I don't want to use 2 because I know what 2 gets me. I got to use a different number because I want to get a very specific result. But I'm going to use -2. Let's do it again with -2 because I want to show something here because there's something more important with -2. Let's do it again with f of -2. With f of -2, I would do the same exact thing. 3 parentheses -2 cubed minus 4 parentheses -2 squared minus 17 parentheses -2 plus 6. This looks terrible. But I got to tell you that this actually equates to exactly 0. It equates to exactly 0. I'm going to type it in my calculator so you can see it. It's going to be pretty awesome. Boom. I'll zoom in right here, and then I'll zoom back out. Zooming in, zooming in, zooming in. Focus. There's the -2 being plugged in, and there's the result at 0. It's so messed up that this thing would equal 0, but what does that mean for us? What that means for us is that f of -2 is equal to 0, and also -2 comma 0 is a point on the graph. That's what that means. And we just looked at the graph before. We just looked at that graph. Let's take a look at that graph, actually. Hold on, I'm going to flip over. Zoom in, zoom in, zoom in, zoom in. Look at that, right there. -2 comma 0. It's a point on the graph. That's kind of nice. I mean, we just spent an entire unit covering quadratics and covering zeros of the quadratic and solving quadratics. This point is a root. It is a solution. It is an x-intercept of this equation. That is what it is. That's kind of nice. I want to show you something that you may have never seen before in your life. This is a historic moment. There are not many times in your life that you can remember when you've seen something that you're like, wow, that was weird. But I want to do that now. I'm going to write down this equation again. I'm using the exact same equation. I want to use the exact same equation. And I want to evaluate f of -4. But Mr. Markey, we already did that. What did you guys get when we evaluated f of -4? What did we get as a result? That's what it should be, and it will be. But we're going to do it differently. We're going to get the same answer. It's going to get you -182. But we're going to do it differently. Here it is. This is the most important thing you will see in this new chapter. What the heck is it? Nah, the bar. It's actually a synthetic bar. Kinda. Which half? The top half or the bottom half? But I have part of the top here. I know, it's on a diagonal. But regardless, check this out. This is a synthetic bar. What does it do? Let me show you. First, I'm going to write these numbers inside of the bar. Mr. Markey, where did those numbers come from? Where did they come from? Except not the variables and not the exponents, the coefficients. 3x cubed minus 4x squared minus 17x plus 6. Those coefficients go on the inside of the bar. There's my -4. This is the number you plug in. This is the number that you plug in. Now, if we are correct, if I do this correctly, I should be getting a -182 as the result. Oop, there's a glare on the examples. I know, I'm sorry about the glare. What did you send? Oh, I'm sorry, you might have sent that like 7 minutes ago. I apologize. Again, I have to keep looking up here or something like that. I know there's not much I can do about the glare other than kind of move this around a little bit. Move this over here. But we're supposed to get -182. What I'm about to do is I am about to do a series of repeated steps. I'm going to do a series of adding and multiplication. Adding and multiplication. And I'm going to keep going back and forth between adding and multiplication until I get to -182. And it's going to work perfectly. But you do a series of adding and multiplication. Adding is always done vertically. Adding is always done up and down. Multiplication will always be done against this number right here, the number that you're plugging in, the number on the outside. Let's see how it works. So I'm going to start with that 3. And I'm going to add that 3 vertically. Vertically to, oh, there's nothing there. 3 plus nothing. It's just 3. Well, that was boring. I know. 3 plus nothing is 3. All right, that was my addition. Let's go to multiplication. I'm going to multiply these two numbers together right here. I'm always going to multiply against the number on the outside. 3 times negative 4, negative 12. Cool. Negative 12. Now I'm going to add. I'm going to add vertically. By the way, look where I put that negative 12. I put it in the first blank spot. I'm going to add vertically. Vertically should get negative 16. All right. Negative 4 and negative 12 make negative 16. Yay! That was addition. Now I got to multiply. I got to multiply now these two numbers together. The negative 16 and the negative 4. Be careful with your negatives and positives. That gets me a positive 64. Hey, do you remember what number we're supposed to get? Yeah. How is that even possible here? Negative 182? Come on. All right, let's see what happens. I got to add vertically. If I add vertically, I got 47. All right. That's weird. Now I got to multiply. I got to multiply these two numbers together, the 47 and the negative 4. What's that give me? 8. Negative 188. Negative 188. But it got me a lot closer. What do I do with these two numbers? Straight up and down. What do I do? Yeah, I got to add them together. Oh, look at that. Negative 182. This is the number you get back. This synthetic bar is going to be one of the most important things that you see over the course of this new chapter. It is going to be one of the most important things that you're going to see. It is going to be phenomenal. Put this over here. I need that for later. Let's go a step farther. Let's do it again. But with that other number. What number did I plug in? It was a negative 2. Let's do it again. I'm actually going to have you do it in a moment. Let me write this down. Synthetic. I wrote it wrong. Synthetic substitution. Let's create another bar here. I'm going to put 3, negative 4, negative 17, and 6. And I'm going to put a negative 2 on the outside. What did we get when we plugged a negative 2 in? That's what you should be getting if you do this correctly. I want you to take a moment. Take like the next 30 seconds. Knock out this synthetic substitution. And if you did it correctly, you should be getting a 0 in that last spot. See if you can do it. See if you can do it. While I organize this stuff over here. See, I told you 30 seconds or less. 30 seconds or less. This paper belongs over here. Take that one and put that on here. There we go. Now it feels better. Okay. Let's see what happens. Now, you did it like so very quickly. I'm assuming just because the numbers just worked out so nicely. Let's see what happens. First, this 3 comes straight down. Multiply against negative 2. You put that here. Then you add straight up and down. You get negative 10. Then you multiply against that negative 2. That's a weird negative 10. Let me rewrite that. You get 20. Then you add straight up and down. And you get 3. Then you multiply against that negative 2. And you get negative 6. And then you add straight up and down to get that 0. What does that mean for us? It means f of negative 2 being the input, results in a 0. Input, output. Furthermore, I have a small definition that I want you to write down. I'm going to write it down as a bullet point. We found out that f of negative 2 is equal to 0. Here's the definition. If f of k is equal to 0, which is what we just had with that negative 2, but if f of k is equal to 0, then k is a, quote, 0 of the function. If f of k is equal to 0, then k is a 0 of the function, also known as an x-intercept, a solution, a root. They all mean the same thing. It's the same definition that we had in the previous chapter. It's just taking it a bit farther. It's taking it a bit farther. Okay, so here's what's going to happen during this chapter. During this chapter, I'm going to be throwing all sorts of equations at you. And I'm going to be expecting you to find out certain pieces of information. For example, let me zoom in on this, and let me type in a new equation before I go back to my notes here. X to the third minus 6x squared plus 13x minus 10. Look at this, look at this, look at this, look at this. I'm going to graph this sucker. It's a weird curved line. That's fun. Oh, again, in the chat, they can't really see it. Let's move that over just a tad. There we go. Maybe they can see that a little bit better now, hopefully. Where would you say the graph crosses the x-axis? Where would you guess the graph crosses the x-axis? Something in that range? Say again? 2.3 maybe? Maybe. I don't know.
It's hard to tell if it reaches the 2.
It's very hard to tell. How many repeat what you said? It's very hard to tell if it reaches that 2 or not, because it could be like that maybe? You know? It says in between. Let's see. I wonder if there's a way we can prove this. Spoiler, yes, there is. Let me show you how. How do we prove this? How do we show? Now, because you think it could be 2. It could be 2. We can prove. We can prove whether or not it is 2. We can do that. Let me zoom out. Write this down. New example. The example that we just wrote down, or that we just had on the calculator, was f of x equals x cubed minus 6x squared plus 13x minus 10. We think x equals 2 is the x-intercept. We think x equals 2 is the x-intercept. Maybe it's 2.3. I don't know. But we can definitively prove whether or not 2 is an x-intercept. And we can do that rather quickly by plugging that 2 into the synthetic division. Hey, what number do I put here? A lot of people miss that. A lot of people say -6 is the first number, but it is definitely a 1, and it's a 1 because of the 1x cubed. It's a 1, it's a -6, it's a 13, and it's a -10. We can prove whether or not 2 is indeed the x-intercept. Once you get the hang of the way that this bar actually works, you can run through something like that fast. You really can. And it's a lot more efficient than actually trying to plug it into the calculator. It's a lot more efficient by doing it by hand like that. The synthetic bar will save you time and energy. This number, the 2, was the possible x-intercept. This number, the 0, this proves x equals 2 is a 0 of the function. Because it's a 0 of the function, it's an x-intercept of the function. Because it's an x-intercept of the function, it's a solution of the function. It's a root of the function. By getting that 0 in that spot proves that x equals 2 is indeed what we were looking for. Yay, it was 2. It doesn't look like it, right? Let me zoom in. It looks like it's curving around really weird. Let me zoom in. Oh, no. Let me zoom in a little bit on the calculator. There we go. If you zoom in about right there, you can see it a little bit better. Yeah. And if I trace it, there's the ordered pair blinking in all of its glory. Fun stuff. Well, fun from my perspective. Well, we all know what I consider to be fun. Staying up for 6 hours on election night just to study math. You guys ever hear of Benford's Law? Oh, man, I'm going to be investigating Benford's Law. Benford's Law has to do with the distribution of the first digit in election results. For example, if a state comes down to like 1.5 million versus 1.3 million, the first digit in each vote total is a 1. Right? If the vote total is like 800 to 500, then the first digit's an 8 and a 5. Benford's Law states that 30% of the time you're going to get a 1. 17% of the time you get a 2. And each successive time down, it gets smaller and smaller until you get to like the 9, which only accounts for like 5% of the time. And you can look at election results on a large scale level, like county by county or district by district, and you can actually graph a candidate's results. And as long as it follows Benford's Law, then the numbers followed a natural progression, and there's no outside interference. Yeah. But if the vote totals for the first digit do not follow Benford's Law, then it could be argued that those vote totals did not occur naturally. Yes, Benford's Law has been around for about 150 years. Everything relates to math. Bullet point. If f of k is equal to 0. This is another important statement that we are about to make. Then x minus k is a factor of f of x. If f of k is equal to 0, meaning that you have a 0 of the function, k is the 0, k is the x-intercept, then x minus k is a factor. Let's talk about an example here. I'm going to put this example on the board in a moment, but I'm going to talk about something very basic here. Quadratic. I want to talk about this quadratic. Oh, I was just looking at the chat again. Check this out. Now, what I'm going to write in red, you don't have to copy down because I'm just going to erase it. So don't worry about copying that down. But let's just say, for instance, that I needed to solve this. I needed to solve this. This is going back to the last 2 months. It's set equal to 0. I have to factor. I can use the Tucker method if I wanted to. Can you give me 2 numbers that multiply to 12 and add up to 7? Sure. Which means x plus 4 and x plus 3 are my factors. But if I were to solve and get the x-intercept, I would get x equals -4 and x equals -3. If f of, now watch this, if f of -4 is equal to 0, which is what this thing does, then x minus -4 is a factor. What is x minus -4 if you simplified it? X minus -4, what the heck? Yeah, +4, because the two negatives together make the positive. It would become x plus 4, which we did know. Now, I'm going to erase this. I'm going to write some information to the side real quick. X squared plus 7x plus 12. The factors are x plus 4 and x plus 3. The zeros are x equals -4 and x equals -3. I'm just going to keep that to the side because I'm going to compare it against what I'm about to do. It's going to be amazing. For me, not for you. So that information in red is stuff that we have been covering for the past 2 months. Look what I'm about to do here. Look what I'm about to do here. I put the quadratic into a synthetic bar. And I'm about to take -3 and plug it in to the equation. That's what the synthetic bar does. It's called synthetic substitution. Going to take that -3 and we're going to plug it into the equation using the synthetic bar. Because -3 is a 0 of the function, what number should pop up right here? Should pop up as a 0. And it will, and it will. 1, -3, 4, -12, 0. Yes, it did. This number right here proves -3 is a 0 and x plus 3 is a factor. That 0 at the end proves that -3 is a 0 and x plus 4 is a factor. There's something going on. There is something going on right under your eyes. A conspiracy that you need to recognize. I have hidden some truth from you. This synthetic bar is used in a process known as synthetic substitution. Yes, I did not lie. But it is also called something else. This process of synthetic substitution is also known as synthetic division. What you have unknowingly been doing is you have been dividing polynomials. You just don't know it. Question. Give me a 2-digit number that's even. Okay, 28. 28 divided by 7 is what? 7. It's 4. Yeah. If you do 28 divided by 7, it's basically you are dividing the 7 out of the problem. You are basically taking that 7 and saying, okay, I'm going to divide you, and I'm going to rip the 7 out of the 28. And when I rip the 7 out of the 28, what's left over is a 4. Is that fair? How do you get back to the 28? You multiply them back together, right? What I'm arguing is that in reality, because this is actually the factor x plus 3, we have divided by x plus 3. Now, I want you to see something, and then I'm going to actually spell it out on paper. Look at these numbers right here. And look at these numbers right here. That's not a coincidence. That is not a coincidence. It's not. That is a mathematical fact, and I'm about to show it to you. I'm about to show it to you. It's going to be insane. Get rid of that. Let's go over here. You ever watch those movies where it's like really confusing during the movie, and then at the end they explain how everything was connected? Yeah. That's what math always is for me. Math is always like that. Watch this. X squared plus 7x plus 12 divided by x plus 3 equals x plus 4. This is the same as the following. This division of polynomials is the exact same process. And I'm writing this down again on purpose because I want you to see it. It's the exact same process as that synthetic bar. It's the exact same thing. It just looks different. Look at the connections between them. The 1, the 7, the 12, they came from the numerator. The -3 came from the denominator. The result was x plus 4, which these numbers seemingly match. Question, when you do division, what do you call the thing that's left over? Remainder. And if two things divide perfectly, what's your remainder? That's not a coincidence. That is not a coincidence. If there's a 3, I'm going to do a little thing that I'm going to erase, okay? Let's pretend for a moment that I tried doing this with positive 3, okay? I know it's not going to work, right? What happens is this. This right here is the same as x squared plus 7x plus 12 divided by x plus 3 equals x plus, it's a 1x plus 10, remainder 42. It didn't divide evenly. We're going to get there. Yes, that question will be answered in the next 5 minutes. I promise. Let me go to this then. Let me add in some stuff. First of all, this number right here is your remainder. That's your remainder. This number directly to the left would be your constant. And this number would be your x term. The result of division is 1x plus 4, or the constant and the x term. 4 for the constant, 1 for the x term, with a remainder of 0, which is phenomenal. Now, the question you were asking is, what if there were like more numbers involved? Yeah. Okay. I'm so excited. Can you believe they let me do this for free? That's the fun fact that I don't really tell my bosses, that I would do this for free just for fun. I mean, look at the Excel spreadsheets that I got going. Come on. But I got to make a living somehow. And I figured, well, I like math and I like making high school students cry. Might as well combine the two. Here's a new problem. I wake up in the morning and I just think to myself, how can I collect their tears and make myself live forever? Almost. You ready for this? The number that goes on the side in this example is positive 2. Because x minus 2 is the factor, but x equals 2 is the 0. Oh, you can't see it. Zoom it out. X minus 2 is the factor. But remember what we were doing over here. Even though these were the factors, the number that goes on the outside has to be the 0 of the function that you're dividing by. There's a clear distinction between them. So I have to put a positive 2 on the outside. I have to. If I don't, it will screw up. Now, it's a 0 of the function. I made sure it was. I made sure that it was. You're going to get a result of 0 as the remainder. But if it's a 0 of the function, then I should be getting a 0 over here. And I will, because I made it so for this problem. I'm going to put a 1, a 2, a -5, and -6. And I'm going to run through that synthetic division. Bring the 1 down. 1 plus nothing is, well, 1. Times 2. Adding, you get vertically, you get 4. Multiply, you get 8. Adding, you get 3. -5 plus 8 is positive. Multiply, you get 6. Adding, you get 0. Now check this out. The result of the division. The result of the division. As I said, this is your remainder, meaning they divide perfectly. They divide perfectly. I said that this was your constant. This was your x term. What would this number be? If I go from constant to x to the first, what would come after? That's your x squared term. That's your x squared term. Meaning, the result of this division, I'm about to show you something amazing in a moment. I'm going to show you something amazing in a moment. It's phenomenal. The result of this division is x squared plus 4x plus 3. That is the result of this division. Let me get rid of that red writing up there. I'm going to draw something on the board in a moment. Everything is connected. Everything that we're doing is connected. Good question. Okay, so the question that was asked is something that I definitely wanted to address. She says, so how exactly do we identify which number will be on the outside in each equation? How do we do that? There are 2 ways of deciding that. 2 ways. Number 1, they'll tell you what to divide by. And then x minus 2. They're telling me to divide by x minus 2. So I got to put that positive 2 on the outside. That's one way of determining it. The second way of determining it. Do you remember when we put the equation up there and I asked you guys, hey, where does it cross the x-axis? And we were trying to guess. We were trying to guess. And you're like, it looks between 2 and 3. Maybe it's a 2.3. Maybe it's a 2. I don't know. Let's try it. We look at the graph, visually identify x-intercepts, and that would be the number that you'd put on the outside. So that's another way of doing it. Let me show you something here on my calculator. Check this sucker out. It's going to be amazing. Check this out. I'm going to zoom in, don't worry. Zooming in, zooming in, zooming in, zooming in, zooming in, zooming in. There we go. Okay. Here is the equation that we just did. In fact, I need to put it in parentheses. Let's take a look at it. Graph. Zaboom, zaboom, zaboom. Check this out. That's a fun noise. I like that. Go away, marker. Oh, that would have been great. All right. My heart can't take it anymore. Anyway, this is the 0, x equals 2, which would be the factor x minus 2, right? Now, we divided it out. In the previous problem that we just did on our notes, we divided it out. Let me show you something phenomenal. Did you ever know a kid in math class that would like literally sleep through everything but still get hundreds on everything? Yeah, I was that kid. All I did was I just messed around on the calculator and I figured stuff out on my own because it was fun. Watch this. This is like one of the things that I would do. I would just mess around with problems. Look, I'm going to divide them. Remember, when we divided them, what did we get? We get x squared plus 4x plus 3. In the previous example, watch this. What do you notice? Because I divided it out. When I took 28 divided by 7, I took the 7 out. When I divided by that x minus 2, I ripped it out of the problem. What else do you notice? Still goes through the same points. It absolutely does. In fact, check this out. The other 2 points here, this is x equals -3, and this is x equals -1, which would be x plus 1 and x plus 3 as a factor. Check this out. I'm going to do it again. But I'm going to leave the x minus 2, and I'm going to divide it by, pick one, 1 or 3? 3. X plus 3. Watch this. I'm dividing it by both of them. 28 divided by 7 is 4. Divided by 2 is what? 2. 28 divided by 7 is 4, divided by 2 is 2. It's like you're dividing 2 different things out of it. I'm dividing 2 different things out of it. But the thing that I didn't divide out of it is still there. It's still there. I just divided out the x plus 3 and I divided out the x minus 2, but it's still stinking there. This was an introduction to polynomials. This whole chapter is going to be focused on problems like this, solving them, graphing them, word probleming them. That's a verb. It's going to be great. Yes, it's a verb. I'm a math teacher. I can do whatever I want. English is a made-up language. No, math is. That's a whole other argument. But mathematics exists outside of the human mind, and I can prove it, but I can't today because there's the bell. Oh, that's true. Everything I teach you is made up by me.